Now, the question this is about, I just sort of do a preface to talk about bonding in general, just very briefly, because there are a couple of aspects of this question that I don't quite agree with in terms of the answer. So, one, generally in temporary dipole bonding or dispersion forces, and a variety of names it seems to be known by, but the bigger the molecule, the more the electrons there are, the stronger the bond. And this can, even though we consider it to be a weak bond, be quite strong if the molecule is big enough. So that's one thing we have to consider, the size of the molecule. Now, permanent dipole bonding exists when we have a difference in electronegativity. The bigger the dipole difference, the stronger this bond will be. Now, hydrogen bonding, in some respects, you could consider it just a really big permanent dipole, but it's a little bit special, and it only happens between hydrogen, of course, and nitrogen, hydrogen and oxygen, and hydrogen and fluorine. Of course, this is not the bond itself. This is just what creates a dipole. So when we have N going to H, and we have a negative there, a small positive there, we'll have an attraction maybe to another negative. And this is the bond. This is just the dipole that's created because of that significant difference in electronegativity. Now, the thing to keep in mind with this is that this is an increase in electronegativity as we go across nitrogen, oxygen, fluorine. And so the strongest bond here, the strongest hydrogen bond, will be with fluorine, then oxygen, and then nitrogen. If you don't know that, that can be a good way of discussing some of the differences in bonding. Okay, so, but there is one other little thing to mention. Now, this is a very simplified kind of structure. If you had a molecule like this and another molecule like this, if they branch, generally, they don't pack as well. They can't get as close together. And if they're basically linear or of a structure that can approach and get close to each other, the closer they can get, the stronger the bond will be. So that's the last thing that you really need to consider, is packing. So if there seems to be some reason that you cannot deduce why there is a difference, packing is often a good explanation. Obviously, when you're looking at the molecule, the one that seems to have a lot of branches coming off it, or some branching, that's more likely to have a problem with being able to pack well. Okay? Now let's have a look at the question. Now, if we look at these molecules, generally speaking, we're talking about boiling point. You should relate this to the fact that boiling point is directly related to the strength of the intermolecular bonding that's going on, and the energy it takes, therefore, to break those bonds. And anyway, when we look at these, the first thing we notice, we go through this, they all seem to have roughly similar size molar masses. They've either got 4 or 5 carbons, and the ones that have got 4 carbons have another oxygen or nitrogen present. So molecular masses seem to be fairly similar. So I would expect the instantaneous dipoles that create dispersion forces, that would all be fairly similar. We do have information about the dipoles there, and as we go down, we notice that there's a fairly significant one here, and then we've also got with OH here and NH here that we've got hydrogen bonding that will be going on there. Okay, and discussing this, you make comparisons between some of the molecules, which and the first one, obviously pentane. The only bonding going on here in this case is going to be instantaneous due to temporary dipoles or instantaneous dipoles. There are no permanent dipoles because there's no significant difference in the electronegativity between carbon and hydrogen, and so that's really all the information there is on this. So it's obviously at 36 degrees. If it's already means probably at room temperature, that would be a liquid. Room temperature is considered to be about 25 degrees Celsius. Okay. Now, before we start talking too much about ethoxyethane, which is also known as diethyl ether, if we look at dimethyl ether here, this is a boiling point of minus 23 degrees, whereas propane has a boiling point of minus 42 degrees. Obviously, propane is significantly lower, even though it's fairly similar in terms of molar mass, etc. The main difference between these two, obviously, is that this has got an oxygen that does create a permanent dipole. There is an actual dipole present, and that would mean it would have a stronger ability to bond. However, with ethoxyethane or diethyl ether, the difference between this and pentane is almost non-existent. It's only about 1 degree difference between these two. So these two are fairly similar. Now, why does this not have too much of an effect? Well, if we have another carbon group on each side, the molecule basically is longer, the chain is longer, and the effect of this oxygen being effectively buried in the middle of the molecule reduces its effect. It's a little bit like some of the alcohols or haloalkanes. I mean, you may, well, not haloalkanes, I mean the acids. You'll get some solubility with a very small number of carbons, but as they get to be bigger, the non-polar chain has a bigger impact on that, and we get a little bit of that. This is not going to have a huge impact. The difference in these boiling points of 36 to 35 degrees is very small. Now, in the answer to the question, they claim that the difference between these, the fact that pentane is a whole 1 degree higher, is due to the fact that maybe this is something to do with packing. I think you'd be better off explaining why this has little effect on this, because you would expect it to have an effect. The fact that the effect of this dipole is basically nullified by having bigger groups on either side of it, I think is more important. Having said that, though, I do appreciate the fact that pentane is higher is a little bit of a surprise, and the only reason that can be is maybe there is a small difference in the ability of pentane to get closer together, to pack a little bit closer. I think both points are valid, but I think this one that they don't mention in the answers is something that you should discuss. Okay, now next we just need to consider the amine and the alcohol. And in answering these questions, it's often a good idea making comparisons between them, because trying to compare one molecule to all five just gets is a little bit awkward, and you probably miss something. But if we look at the amine and the alcohol, similar molar masses again, a big difference here with the fact that the alcohol has a much higher boiling point. And we get obviously an increase in the dipole here, and that's really indicative of the fact that the OH group here, as compared to the NH2, we get the oxygen is more electronegative, and we get a stronger, bigger dipole between these two. So that's going to be bigger, and that means its attraction to another molecule is going to be stronger than it would be for an amine to another amine. So just the fact that the oxygen is more electronegative, creating a stronger hydrogen bond is important here. Okay, now the next one is probably more of a shock, and that's the butanone. We've got a really high dipole here. Now that kind of difference in polarity you would think would be enough to cause a fairly high boiling point, in fact the highest of all of them. And the fact that it's about 80, which is higher than the amine, but we still have butanol being higher, significantly higher than it is. Doesn't it really, it's hard to reason that one through. The oxygen would appear to be partway through the molecule as well. And what this is really down to is the fact that the dipole is due to the fact that double bond to the oxygen here there's a lot more electron density here with having a double bond, So we're going to have a more polar bond. It's certainly a lot more polar than a single bond to the oxygen, and therefore, why don't we get a significant increase in boiling point? Well, this is down to, and you've got to logically work this out. There's only a few things, well, there's only one thing really left, and that is to do with packing. How do they pack? And when we look at this, if we have a carbon double bond oxygen and we have other groups on the other side, and those three groups mean we in effect have a 120 degree bond angle. It's a trigonal planar shape. If we look at the molecules there, they typically always have four groups or four sets of bonding or non-bonding electrons, or whatever the case may be. Basically all the others are tetrahedral. So obviously this trigonal planar shape, due to the carbonyl group here, means that they obviously can't pack as well, and therefore the boiling point's not going to be as high as it should be, or should be, but you would expect. Okay, and that's that question really answered, as long as you explain those, detailing the difference between them, and being very comprehensive in your answer. You should get good marks for that, and that's that part.